So hi everyone, and welcome to this new seminar. Today we have the pleasure to hear from Justin Feng from the Institute of Physics of the Czech Academy of Sciences in Prague. And Justin will be here for the week, so feel free to talk with him also during the rest of the week. The topic today will be event horizon termination and the emergence of Lorentz signature. So feel free to ask questions during the talk. There will be time at the end as well. And Justin, thanks a lot for being here. You have the floor.
All right, thank you. So I'm going to talk about some work that I've been doing over the past few years, and it's really I guess a summary of what we've been doing in these three papers. So this is work that was done in a collaboration with Shinji Mukoyama and Sante Carloni for those first two papers. The most recent one, which just got published, I believe on Monday. So I finally was able to update that reference. That one was done with Jean-Philippe Bouzon and currently Will Barker, who is also at the Czech Academy of Sciences. He is joining in on current ongoing work, which I will briefly report on. So get into it. So maybe before I jump right into it, I should mention that this project, it kind of started as a bit of an arts and crafts project. And so that's kind of the story about how it originated. And well, it actually goes back a little further than that because when I was a postdoc at Centra in Lisbon, we had a visitor. I remember Carlo Rovelli had visited, and he presented this diagram, and he was pointing out that that in this conformal diagram for an evaporating black hole, there's this particular point that you need to pay attention to. So the basic idea here is, well, you basically do a conformal compactification of Schwarzschild space-time. So basically you you have a function that brings the boundaries at infinity into a finite part of this diagram. So each point in this diagram corresponds to a two-sphere, and you can imagine this as kind of a compactification of the radial and time directions of the Schwarzschild space-time. And so what this describes is, it describes the formation of a black hole. So the horizon forms at some point, and then of course it continues. And if the black hole evaporates to a horizon area of 0, then naively you might expect the horizon to just terminate. And so that's what this diagram is describing. This surface here, so that I'm imagining a Schwarzschild-like black hole, so no rotation. So I have a space-like singularity in this particular diagram, and so of course the question is, what is the end state of an evaporating black hole, and in particular what is the nature of that horizon termination point? And of course the arts and crafts project involved cutting this diagram out and then just trying to cut and paste things together to kind of get a sense of what's really going on. And of course, I will illustrate exactly what goes on in subsequent slides. So so I should mention that there is a literature. There is a literature of regular black holes, and of course, it does involve regularizing this surface. And I think in a lot of that literature, there really isn't a strict horizon in the sense that I'm considering it here. So there's something that looks like a horizon, an apparent horizon, but then things can ultimately escape. So that's the difference between what I am doing here and what is being done in the regular black holes literature. So now I'm going to jump into a topic that seems almost completely unrelated. So this is the trouser space-time. And the trouser space-time, it was something that was studied by Anderson and DeWitt. And this was, well, originally in 1986, and they were basically trying to figure out, well, what happens to quantum field theory in the presence of topology change. And so, of course, the topology changing spacetime they considered is the Trouser spacetime. And, of course, the Trouser spacetime, you can construct it by taking a piece of 1 + 1 Minkowski space. The time direction is up, space direction is horizontal, and of course C is 1, so 45-degree lines are the lines on which light rays travel. And so you can construct a Trouser spacetime by taking a 1 + 1 Minkowski space, and then you basically cut it out, and then you identify the sides as indicated. So these two black dashed dot lines, these are identified or glued together. These lines are glued together, and these lines are also glued together. So I've color-coded them and also labeled it with identify. And so the construction is, well, you can actually do this on a sheet of paper. You could basically take a sheet of paper, maybe print this diagram out, and then you basically fold it in on itself to create something that kind of looks like that. And then, of course, you can think like a topologist and smooth out all the creases and bend and twist it until you get something that looks like an upside-down pair of pants. So that's a Trouser spacetime. And so you might see that here I've sort of highlighted this area around the point at which the paths slip. And of course, I've labeled each of these regions with numbers, and so the labels indicate what is glued to what. And so this region 1 is glued to region 2, region 6 is glued to region 7. And then, of course, as you do this construction, you'll see that at the point where this split occurs, you get 2 future-directed light cones and 2 past-directed light cones. And so this is necessarily a singularity because everywhere in this manifold you only have 1 future-directed light cone and 1 past-directed light cone. And so this is a rather severe change of the causal structure of the space-time at that point. Of course, this particular point, this is a technical term. This is something that they actually say in the literature. It's called the crotch singularity. And it happens to be big. Anyway, so how does this relate to an evaporating black hole? Well, what you can do in the 1 + 1 setting is you can actually just draw out the full conformal diagram. So this is the full thing in 1 + 1, and of course, because it's a 1 + 1 diagram, I can just paste it onto the Trousers spacetime, and of course, you can think of it as being somewhat conformal to the Trousers spacetime, because, well, I mean, in 1 + 1 dimensions, you have local conformal invariants, and so I could just paste this into some sub-region of the Trousers spacetime. And in this case, you can kind of see what's going on here. So if I decide to smooth out that singularity, sigma, then of course you can imagine that space-time will continue into the future, and then of course, because the horizon terminates into a point, this region in the exterior has to be causally disconnected from whatever is happening in there. And so basically, what you would do in the 1 + setting is you would basically glue this region, which is originally here, to that region there. But of course, the interior is just some other region that kind of separates off. But what's nice about the trouser spacetime is it tells you the nature of that termination point, and it is in fact in this setting it's the same type of singularity as you get at the trouser spacetime. You have a doubling of light cones. Now, of course, this is not unique. You can always what you can do is, in principle, you can imagine gluing the interior of this interior thing to maybe some other region. And so you can, in principle, glue a bunch of different, patent legs together, and you can create a many-leg trousers type of topology. So it's not entirely unique, but this construction, it gives you a hint as to what the horizon termination looks like. And my claim is that if you want to study these horizon termination points, you should look at singularities like the type that you find in the trouser spacetime. And so before I guess get a little bit further into I guess the nature of these singularities in detail, I'll just do a brief aside and kind of give you a sense of how you might generalize this to higher dimensions. So of course this is all done in 1+1 dimensions, and of course what you can do is you can start with these diagrams, and you can just imagine placing a scalar field with level surfaces on top of this diagram, and of course you can set it up so that the level surfaces of the scalar field correspond to constant radii for a higher dimension. And so this is one way to sort of think about how you might generalize it to higher dimensions. One thing that I want to point out is that you do have something non-trivial that happens in higher dimensions. And so if you look at the causal paths to that point, you find that, well, in one direction you have null rays that are tangent or that go along the horizon, but then of course you have another set of distinct null rays that go out to that go back to past null infinity. And so what this indicates is that you have two classes of null curves that are in a sense disconnected with each other, and so naively you might think, well, it looks kind of like a past light cone, except that the topology of the causal paths of S is not a light cone. So that's a subtlety that I want to point out here. But anyway, so of course I talked about the singularity, I've described it, but this type of singularity, so this type of singularity, it has the properties of I guess saddles, or of saddle points in dynamical systems. And the way to see that, so going back to the 1+1 setting here, the way to see that is that you can construct this type of singularity, again, with a cut and paste procedure in Minkowski space. So basically you take, a disk in Minkowski space, and then you sort of cut it, and then you glue it together. And here I have a non-conformal diagram. So basically I stretched and swatched the disk so that that I can put the whole thing on a sheet of paper. So this blue is the future directed light cone, and these hatched regions, those are the past directed light cones. And if you draw out the general direction of time in these regions, well, what happens is that these time directions, they flow in a manner that resembles a saddle point. And so that's why this is kind of a satellite singularity. And of course, later on,
what's the arrow stands for what? Sorry?
It's the direction of time.
Okay.
So it's a general direction of time. And of course, another thing I would like to point out is that I've drawn this null curve here, and basically, when you sort of squish and swash it, the null curves get bent near the singularity. So, yeah. So this is a more detailed look at the type of singularity that you get at the trouser spacetime, and of course there are further generalizations of this, but they fall under the general classification. They're generally called quasi-regular singularities, and these are things that of course you can form them by a cut and paste procedure. And in fact, you might be familiar with one. This is a conical singularity, and it is a type of quasi-regular singularity that is also formed from a cut and paste procedure. So basically, you take a disk, you cut out a wedge, and then you glue the interior lines of the wedge together. And of course, these singularities they're not that incomprehensible. I mean, you can see that there's a concentration of curvature there, and so all you do is you just draw a loop, and then you can parallel transport a vector around the loop, and of course, since it's flat, you know how to do it locally. Of course, because of that angle, you'll get a deficit angle if the loop encloses that tip. And of course, if you want to regularize it, it's pretty straightforward. You just smooth the tip, and then maybe you can make it like part of a sphere. And so these things are somewhat understandable. And so there's this work by Ellis and Schmidt who generalized it. It includes this satellite singularity, and of course, this work by Ellis and Schmidt also includes further generalization. So, for instance, you can not only glue two copies of Minkowski space together, but you can glue multiple, even more. So 3, 4, and you can have many different light cones, many distinct future-directed light cones from the same singular point. Of course, this is something that Ellis and Schmidt studied. I guess maybe I should mention the definition. So these quasi-regular singularities, the way they define it is, so of course, you can imagine singularities as points on which inextendable geodesics terminate. But a quasi-regular singularity is one in which the curvature remains finite or bounded as you approach the singularity. And in fact, in this case, the curvature is 0 all the way up to the point where you hit that singular point. That's
Can I ask perhaps a very naive question? So in this trouser diagram that you showed earlier, it reminds me of the diagram of the event horizon collision of two black holes. So does it mean that there is such a singularity also?
I think I've seen some talks discussing that. I'm not sure if those are the same types of singularities as the ones that you encounter here. So of course, what I'm thinking about in these diagrams are spaces that are I guess having Minkowskian tangent space at every point. For a horizon, the tangent space has a null direction, and so I'm not entirely sure how those singularities behave. But maybe it's some generalization of these quasi-regular singularities. And so anyway, these types of singularities, they're just quasi-regular singularities, and they're not completely incomprehensible. So don't fear these singularities. And so if you want to get a sense of what kind of fundamental physics might give rise to these singularities, there is a construction that of course it appears quite often in modified gravity theories under the guise of these disformal type transformations. And so of course, a conformal transformation is one in which you scale the metric by some scalar quantity. And then, of course, you have these disformal transformations, which also include the addition of the addition of the product of two gradients of the scalar field, and so here I've considered a rather simple disformal transformation of the metric, and if you choose the scalar field to have this saddle-shaped profile, then what you get is something that looks like this. So what I've drawn here are the level surfaces of the scalar field. The direction of the arrows correspond to the gradient of the scalar field. And you can in principle choose a gauge in which the scalar field is a time coordinate. And so you can imagine these as being, for instance, the level surfaces of some particular time coordinate. And of course, if these gradients are sufficiently large, then they can change the sign of the metric in the direction of the gradient. And so the idea is that you start with some Euclidean signature metric, and then you place a scalar field on top of that, on top of this Euclidean signature geometry, and then you construct this effective metric. And this effective metric can acquire a Lorentzian signature in regions where the gradient is sufficiently large. And so in this particular example, so this is just flat Euclidean space with a satellite profile. As it turns out, in these I think it's UV, in these UV coordinates, the surface on which the metric becomes degenerate, where the signature changes, it's actually a circle for this particular choice of profile. And if you look at the direction of time, as indicated by the direction of the gradient, then basically in the horizontal direction, time is flowing inwards to the singularity. In the vertical direction, time is flowing outwards. And so if you zoom out, this looks like the type of satellite singularities that we saw in the previous slides. So that's a potential microscopic description for these types of structures. And what's remarkable is that you can actually find a theory which actually admits this as a solution. Of course, there is a theory that admits this as an exact solution. I'm not entirely sure how realistic it is, but there is a class of theories that admits this as at least an approximate solution. And so here it is. So this is a theory that was proposed by, well, the general approach was proposed by Shinji Mukuyama and Jean-Philippe Luzon. And so basically they had this rather remarkable picture of a universe which has these, Lorentzian patches and Euclidean patches. And I'll show you a picture of that later. And I think Shinji Mukuyama, he basically wrote this paper. I think this was sort of in the wake of the Korjava-Lifshitz gravity, when it was very popular, and so I think that kind of overshadowed this theory. So of course, when I first encountered this paper, it was quite remarkable. I thought it was a great paper, but it only had 10 citations at the time. But the idea is you basically postulate a Euclidean signature metric with a scalar tensor action, and of course, Shinji proposes that this action is bounded below, and then of course the idea of Mukuyama and Luzon, they basically they basically postulate that in the appropriate regime, the matter couplings are all coupled to this effective metric. And so, they propose couplings such that the dynamics are as if the matter couplings are to this effective metric. So you don't just take a Lagrangian and just replace the effective metric. There's a particular choice of couplings that effectively does that for you, but you don't necessarily see it right away. And of course, the reason why I'm making this distinction is because if you sort of do it naively, I remember talking to Richard Woodard at one point, and he basically said, well, these can't be renormalizable, and so. And of course, the reason why Shinji wants to do this is because he wants something that is renormalizable. Originally, he proposed a power counting renormalizable theory. And later on, Luna, Yuki, and Wata showed that a theory of this form is, they showed in a more, I guess, rigorous manner that this theory is in fact properly renormalizable.
Sorry, I'm asking, this theory also cost-free?
Well, the thing is, if this is Lorentz signature, it is not cost-free. But Shinji's way around it is to say, well, this is Euclidean signature. And so what you can require instead is that the action be bounded below. And of course, there's still an issue of, well, how you quantize this thing, because of course, how do you even define a notion of unitary time evolution if your time is dynamically determined? It's an interesting question. Of course, we haven't really explored that.
And Justin, what's the motivation to postulate these non-standard matter couplings in terms of this effective metric?
Yeah. So the general aim, the general thrust of this work is to basically show how time can emerge from a fundamentally Euclidean geometry, and so basically it's a model for emergent time. That was the general picture
so this postulation is such that there can be a signature change for this effective metric.
Yes, and so basically they're dropping the assumption that the manifold is fundamentally Lorentzian. Yeah, but basically that what we see as Lorentzian is really just a manifestation of these couplings. That's their
How does the equivalence principle
That is a very good question. And I think it is actually still, it's a question that, as far as I can tell, is still open. I mean, I think, so, I mean, if you're thinking in terms of field theory, what you need some mechanism to sort of force all of the couplings to effectively couple to the same metric. And of course, you might think, okay, maybe you need some sort of fine tuning or some sort of other mechanism. Shinji has pointed me to a paper which claims that you can get something like this emerging. I can't for the life of me remember that exact paper. Is in nuclear physics from the 1980s. I can look it up later if you're interested. But as far as I can tell, this is still very much an open question as to whether you can imagine some mechanism that I guess forces the matter to effectively couple to the same metric. So yes, so recovering the equivalence principle, that is a key issue in this approach.
Sorry,
Yeah.
can you go a few slides before? So, and where exactly in these, that is not subtle points.
Yeah.
So where exactly do you have the metric, the signature change is inside the circle?
Yeah, so inside the circle, this effective metric it's Euclidean, but then as the gradient increases, so it increases as you go out from the origin. As the gradient increases, then you get that signature change.
So is there I was wondering about some solving some wave equation, so you have some initial data, you have some sort of Cauchy horizon in this case, so how does it work?
Well, so I guess the picture here is that you would not really solve hyperbolic equations. At least fundamentally, you don't have hyperbolic equations. Fundamentally, you have perhaps equations that are elliptic in nature. And so really what you would do is you would basically specify some boundary conditions, and then you would solve the equations inside the domain. And you have some regions in which you get this effective Lorentz signature, and in those regions you can perhaps reformulate the problem so that you can write the equations in terms of, you can write the equations as hyperbolic equations and solve the Cauchy problem there. But the picture here is that fundamentally that's not what is going on.
So it's a controlled loss of hyperbolicity in a sense. It's intended rather than a pathology of a theory, right?
But imagine that you have initial data.
You have to solve it by the boundary conditions that you put on the rest.
So you need extra data on that.
That's right. There's no time inside, so. But it's intended. But probably the recipe. So what's the recipe for the boundary conditions that you put there?
Well, I will maybe give a sort of a partial answer in a bit. So anyway, so that's the theory, and of course, as it turns out, if you fine tune the parameter, you can get this as an exact solution. But if you don't want to do any fine tuning, then what you can do is you can basically start by getting the field equations. So they're rather complicated.
Can I just ask, Danny, you have a very complicated scalar tensor theory, right? But you could postulate this matter coupling, which is not trivial, and at the end of the day, it's what's going to give you this transition in a simpler scalar tensor theory. So why? I mean, this is actually a very general theory because it has many possible couplings.
I think it's.
Do you need this very complicated theory?
I mean, well, the thing is, you don't need this complicated theory. It's just what I had access to, and of course, I kind of like it because it's the most general thing that you can write with that has shift symmetry and also has up to 4 derivatives of your field. So so you can basically motivate this with general principles. But of course, in practice, you would actually solve something similar unless you do things numerically. But of course, I mean, these are some rather complicated equations. I think I only looked at a few simple instances of this, but in principle, though, if you look at this, it contains up to 2 derivatives of the Riemann tensor, and so you can actually find some Riemann normal coordinate expansion. So basically, you expand about a certain point. And you start with, of course, locally flat coordinates, and then you go out from that point, and then you basically get an expansion that involves, the Riemann tensor and its derivatives if you go to higher order. And so in that expansion, basically what you can do is you can say, well, I just want these to be satisfied at the origin. So I basically want the origin value of the curvature to satisfy these equations at one point, and then basically you just choose the coefficients of your Riemann normal coordinate expansion that way. So in this way, even with general parameters, you can turn this thing into an approximate solution. So you can make this work at least in the neighborhood of the point. So anyway, these are the equations in their full glory. They're a bit complicated, but I guess I want to point out one thing is that because you have shift symmetry, the equation for the scalar actually simplifies to something of the divergence form. So actually, this phi is a source, analogous to the t. But if you don't have any sources for the scalar field, then it's just the divergence of this current, and its current is not too bad. And And so that sort of finishes the first paper in the series, and then there's a second paper which sort of starts with a question that Shinji posed, and he basically asks, well, can you be fooled into thinking that a fundamentally Euclidean theory is Lorentzian? And so we're not really thinking so much about the matter couplings as much as we're looking at just pure gravity and whether by studying this, can we see things that look like they satisfy, that propagate as if they are, or behave as if they are propagating on a manifold Lorentzian signature. And so the setup is, so of course, we started by reparameterizing the Lagrangian, but the setup is that we're doing we find some simple background solution. So this is just flat, and of course, we basically get Minkowski space if we choose this to be, I guess, our Euclidean metric, and then this to be the profile of our scalar field. And we're just using standard Cartesian for this route. And of course, this we've introduced an extra field chi. Basically, this handles the R squared term. So if you do the auxiliary field variation, then you get the same equations of motion. And so we start with some flat background solution, and then we basically do a perturbation. And to simplify things, we just look at modes going in one direction. So it's about a simple setting that you can imagine. And so basically you can decompose this into some tensor modes, some vector modes, a bunch of scalar modes. And of course, I think some of these, in principle, you can also, well, I remember at some point, some of the scalar mode or scalar quote unquote degrees of freedom actually turn out to be non-dynamical, and then you can integrate out a good number of them. And but anyway, the idea is you pick a particular mode, and then you perform the variations. Well actually you pick a particular mode and then perturb the action, and then you take the long distance limit. And in doing that, what you find is that after I guess carefully looking at each sector, so I think this vector sector, it turns out to be a massive Euclidean. It satisfies a Euclidean dispersion relation, but it has a large tachyonic mass. And so what that does for you is basically you can basically tune if the tachyonic mass is large enough, then basically you can suppress it by the appropriate choice of boundary conditions. So basically you choose boundary conditions, and then and in fact you can choose vanishing boundary conditions to make this vanish. And that's of course because it's a fundamentally I guess elliptic degree of freedom. And of course, because we're doing things at the linearized level, we do have properly elliptic equations for some of these modes. And I think you can basically do the same for the scalar fields. It takes a lot of work to basically, so you can't exactly decouple the scalar fields in a straightforward way. And so there's kind of a trick that you have to employ. And basically, the idea is you work out the equations of motion, and then you take the determinants, and then you basically identify each of the factors in that determinant to get the dispersion relations of the degrees of freedom that are mixed in the scalar sector. But anyway, it's complicated to deal with. But what we find in the end is that the scalar modes you can choose parameters such that the scalar modes all satisfy Euclidean dispersion relations, so they effectively satisfy elliptic equations, and then basically you can deal with them by choosing the boundary conditions appropriately, and you can choose everything in such a way that the tensor modes still satisfy a Lorentzian dispersion relation. And there's still a rather large region of parameter space in which you can do this. And so because the tensor modes satisfy a Lorentzian dispersion relation, then you can be fooled into thinking that that this theory gives you some, you can be fooled into thinking that some of the degrees of freedom propagate as if they were on a Lorentzian background. So this is of course, a very preliminary result, but it at least shows that in principle this is sort of, well, the answer to the question is in the affirmative, at least in principle. So anyway, I didn't realize I was going that far ahead of time. So I will focus on pictures then, which is this rather amazing picture that I think this picture, as well as another one that appeared in an early paper with John Philippe, these are sort of the imaginations of John Philippe, and I always like discussing with him, because every time I talk with him, it's like, he paints a lot of really neat pictures in your mind. And so so basically the picture here is that you have, regions in which you have these so basically you have this Euclidean sea here, so it's in blue, and then you have these pockets in which the gradient is large, and so then you have these Lorentzian pockets, and his idea is that our universe lives in one of these pockets, and that the Big Bang is actually the boundary of one of these pockets. And so here you have these zoomed in pictures. You have one in which you have this mirror universe where you have you kind of have this Euclidean isthmus or something. So just or a Euclidean straight, since I'm saying Euclidean sea. So it's a Euclidean straight, and then of course you have a scalar field with gradients moving in both directions, and then as you move to the edge of that straight, basically you get this Lorentzian region, and that boundary is the Big Bang in this picture.
Is it not quadrifractal?
Huh?
Is it not quadrifractal?
This picture is
No, fractal structure. It doesn't appear in the system.
I don't think we've encountered that, but that's an interesting consideration.
Fox counting dimension to see.
Oh yeah, maybe. I mean, that's something that we haven't considered, but it's an interesting thought. And so basically what we did was we looked at a simpler version of the model for this. For this, we just wanted to do a proof of concept to see if it worked. And so no point in working with this really complicated system. And so this is much simpler, and of course it might be somewhat familiar if you've worked with Horndeski or scalar tensor type theories. And I think, of course, we have this G4, which is related. Yeah, it is in fact the same type of G4 that appears in Horndeski. And so we have this this model. We looked at a plane symmetric geometry, and also a plane symmetric scalar field, and when you work out the field equations, you can actually write them in this form, which is kind of nice. Basically, you define this script G as this combination of G4 and its derivative, and you can really simplify the equations into a nice compact form, and that will become important in just a bit. And so basically, you can do a rather simple Einstein for this. You have a linear G4, and then you have a quadratic strip K, and then you can just solve the system of equations, and then you can get this as one of the solutions. And so basically what happens is, if you look at this, this lower curve here, it's G00, and it's negative initially, but then it flips sign here, so it's positive up there, and then it goes negative again. So this is your effective metric. And of course, you have a mirror universe. You have two Lorentzian regions that are connected with this Euclidean region. And of course, so we also looked at the late time behavior, and it does behave as you would expect a de Sitter space-time to behave. And so you have this late time de Sitter phase that appears. So it's a nice proof of concept. And actually, this form of equations is rather suggestive because what you can do is you can actually read it differently. You can basically say, well, let's suppose I have an expansion history for the universe. I feed that in to the equations, and then what I get is I get a set of equations for G and K. And so basically, you can invert the field equations, and then basically you can try to reconstruct your theory from a given expansion history. So this is another interesting thing that you can do with this model. So it's a very flexible phenomenological model. I'll let you decide whether that's a good thing or not. And then, of course, this is some ongoing work. Of course, whenever you work with a new class of theories, you want to look at the cosmologies, and then of course you want to look at the compact objects. As far as I can tell, the compact objects in this class of theories hasn't really been studied all that much, but we do have a preliminary result. And basically, if you consider again this second order theory, we basically search to see whether Schwarzschild solutions fit, or at least whether we can recover Schwarzschild solutions in this theory. And it turns out that it just amounts to a very simple criterion. You just need to make sure that that the root of this K occurs at an extremum or a critical point of K. So as long as the root and the derivative vanish, so the root can either occur at the minimum or maximum of K, or even a kind of a saddle point, then you can get a self-Schwarzschild solution. So anyway, that's a preliminary result from some ongoing work that we are doing with Will Barker. So anyway, that's something to maybe look for in the coming months. So anyway, these are the takeaways, and since I am perhaps approaching the end of the hour, I will leave it here. And here's some snacks.
Thank you very much, Justin. So we do have time for more questions, if there are any. Maybe the Eugene.
You mentioned the Sitter space-time.
Yes.
The Euclidean solution.
Yeah.
Do you have any connection with the proposal of Hawking after we no longer context way of the universe, emergence of time in this context?
Yeah, so actually one of the things that we had mentioned in this proof of concept paper is that this is a way of realizing a type of no boundary proposal. Of course, as far as we can tell, we can't quite get the solution, or at least a picture that you see in a lot of these papers where you have this universe and then it's sort of capped off by a sphere. We couldn't quite get that. That was something I was hoping to see. I couldn't quite get that to work, at least not in this simple model. Maybe with a more complicated model you can do it. But at least more generally, this is something that in principle can be done without having to actually go to a fully quantum theory. This is something, so everything that I've done, of course, maybe some parts of it are motivated by perhaps, quantum gravity considerations. Of course, talk about renormalizability, so there's, some potential that maybe this can be a way to UV completion, but other that aside, this is all classical. And so in principle, you can kind of realize the types of things that Hawking and Hartle were thinking about, but within a fully classical context. So that's the utility of this approach.
Well, I was going to ask the same question about the relation with the boundary. But, well, I mean, in that case, you have an imaginary time. That's how they describe it.
Yeah.
Here, there, you have these several patches with no time. So there seems to be similarity.
Yeah.
But, and of course, as you're pointing out, I mean, this is sort of all classical. So there is no fundamental embedding of this model. Scalar field is, part of the scalar tensor theory, but it doesn't have any fundamental origin. And the key thing seems to be this formal coupling at the end of the day.
Yeah.
So my question now is, well, couldn't you just start with a very simple theory like Einstein minimal coupled to a scalar field, a real scalar field? And I just assume that I'm working on Euclidean section. But then I say, as you said, that matter couples to this conformal metric. So in any solution that I get to this Euclidean theory, simpler than yours, because it doesn't have non-minimal coupling, I could play the same game. I could see regions where the gradient of the scalar field is large enough such that I get, Lorentzian patches. So why wouldn't that be as well motivated as this theory that you are considering?
Yeah, well, I mean, I think that was actually the original approach that Shinji and John Philippe were exploring. I think they were looking at theories that look kind of like this. Of course, I guess the reason why they were looking at this particular one is because they wanted something that was general. And I think this, or at least it was general enough for their purposes. But yeah, you could have a much simpler theory. I agree, and play the same game. I guess the reason why I wanted to consider that the other theory was just because it had some nice properties as well, if you're thinking in terms of, well, what could be a UV completion for gravity, then that other theory has some nice properties. But I agree, you don't need to go all the way in order to realize this type of mechanism. Yeah.
And another question is a natural way in which these formal couplings emerge is in collusive theory, actually, because you have that the lower dimensional metric is related to the higher dimensional, then there's always an extra piece. So I was wondering, I mean, in playing with the signatures in the higher dimensional space, you could get some, perhaps one actual setup in which this could emerge.
Yeah. So I haven't looked at the particular case of collusive Klein theory, but I guess one thing that I was also sort of exploring, at least in the context of these models, which go under the name of embedding gravity. And so the idea is that you have some really high dimensional space, and that GR is basically lives on a 4-dimensional submanifold of within this higher dimensional flat space. And then of course you can construct a model with these embedding functions that satisfies the Einstein equation. So basically you can construct the Einstein-Hilbert action out of that. And so I think in that setup, you can also get these similar trousers space-time type constructions. And so you can get the kind of singularities that I showed you earlier. And so that was something that I was looking into, but I can't say that I've explored that far into it. And perhaps maybe there's something else that you can do, for instance, with D-branes. But yeah, that's a bit beyond my area of expertise.
Are there other questions? Well, maybe I have one. Also, more coming back to the trousers space-time part. So, what you were saying, I don't know, or mixed with the end, right? You were saying that with this sea of Euclidean space and then these two emerging Lorentz parts, is there a singularity of this type, like in the middle, like you had this picture at some point with the simplified model?
Yeah.
And is it something that we could, I don't know, observe in some form or like you related it to the Big Bang, for instance?
Yeah. So I guess the pictures that I was showing later on were with these Euclidean pockets. Yeah, these. So of course the underlying topology of the manifold is just RN, and so in order to get something like a trousers type space-time, you do need So if you want something that globally looks like the trousers type space-time, you do need some sort of topology change in the manifold, and so that's something that would have to happen at the level of the Euclidean metric. And so of course, at least the thinking there is that perhaps you have the thinking there is perhaps you have some non-trivial topology that's allowed in the underlying metric.
Can I perhaps ask a very silly question? So you have these sort of mirror universes. Would you expect some kind of quantum correlation between them? Between events in one and the other?
Yeah, that's a very good question. I haven't really thought about that particular one in detail. Maybe John Philippe has, but again, as I said, this analysis that we've done so far is purely classical. But it is a very interesting question. I'll ask John Philippe if he's considered it.
Could you communicate with this mirror universe?
I was actually thinking if there is some sort of correlation. Perhaps the dark matter is there.
Well, the dark matter
No,
is
dark
there,
matter, no,
that's
the antimatter. So
yes.
kind of symmetry.
It connects to this multiverse idea in a sense also, right? So
I mean, if I want to venture really far out into crazy territory, as I sometimes do, I mean, since basically, it's a fundamentally Euclidean problem. I mean, you're basically what we do in our present time, sort of, you can think of it as a boundary condition, right? And since these satisfy elliptic equations in motion, I mean, maybe what you're doing here can affect what the solution's back there. But of course, this is way out there. I should be careful not to allow myself to venture out at least not in a public setting like this.
over lunch.
Yeah, over lunch.
Yeah, please.
So there are some studies with Einstein gravity for dimensions. Einstein gravity, Gauss-Bonnet, scalar field, some coupling with the loss of hypervelocity when doing evolution. By reaching some Euclidean region space-time, but this is for black hole physics, Pretorius, and also perturbation theory. So it's one to point out, is it any connection? So it's again, the system is different. But we notice problem with hypervelocity. We start with hyperbolic problem, normal time, and then we move to some region of information and get the living content in the gel plot.
It's an interesting thought.
It becomes elliptic inside the black hole. Then in that case, it jumps out of one.
Yeah, but effective metric is not like this. So here the point is that you have this coupling. It's this metric, G mu plus the gradient mu phi. So that's not the effective metric because that basically it's actually space-time metric. That's ruling the evolution, but it's not as simple as the gradient, G mu gradient.
But you start with R-square gravity. As time is generated by this transformation of the metric, did you arrive at Einstein gravity at the end?
So this is something that I did gloss over. It's not exactly Einstein gravity, but but there is an argument that that if you take the long distance limit, I forget. I think there are some additional assumptions that you need to make, but you start by taking the long distance limit of this, which sort of gets rid of, higher curvature and some of the higher derivative terms. And then you can argue your way to a model that looks like that. And then of course you can basically apply this formal transformation within that model to get something that looks basically like this, but with the Lorentzian signature and with a particular set of relations between the G's and the K's. So
curvature which is complex to the scalar somehow.
yes, but I guess the idea is that at least in the Lorentzian sector, that you basically set up this potential K such that you have some sort of symmetry breaking, and so that at least in some parts of the Lorentzian pockets, this effectively becomes constant. And so that's sort of the general picture there.
All right, so we've had a few questions, and Justin will be here for the rest of the week, and for lunch. So if you have more, you can take this opportunity. And for now, let's thank Justin again.
And please take this off.